Welcome back to part 3 of our lessons on bond length and resonance structures. And the last part is going to be formal charge. Now, formal charge ties together Lewis structures and kind of potentially different ways that you could draw them to stuff that we've been previously talking about. So formal charge is kind of the last thing that we're going to have to talk about when we draw a Lewis structure. What we'll be getting into later is going to be what to do with that Lewis structure after you draw it. So formal charge deals with situations where you can potentially draw more than one valid Lewis structure, and it ties back into potentially resonance structures, but more often it ties into situations where you could have two compounds with the same chemical formula, but a different arrangement of the atoms in the actual molecule. And so you do see that once in a while when you get into molecules, especially that are larger in size. So molecules that have two different centers or multiple centers, or you can get kind of branching that happens potentially in drawings. And so sometimes you can actually draw more than one legal Lewis structure. And as long as it follows all of the rules for the octet rule appropriately, you can have more than one Lewis structure. And so when that happens, you have something called an isomer. Isomer means the same parts, which means that it's made up of the same atoms, but it has a different structure. And an example that I have here is that of butane and isobutane. So both of them have the same chemical formula, C4H10, but they have different structures to them. So butane is kind of a straight line, whereas isobutane has a straight line and then a branch coming off of it. What ends up happening is that these two are both valid Lewis structures, and in fact, they are different compounds that exist. And when you have two different compounds that actually exist, you get different chemical properties. Sometimes when we draw Lewis structures, though, things get kind of crazy, and we have to decide if one of them makes more sense than the other. So here is another example. Which Lewis structure is more likely? This is sulfuric acid, by the way, and you can draw it like we can on the left here with two double bonds coming off of the sulfur. That is totally legal within the Lewis structure rules, as well as this right one where it's all single bonds. The number of valence electrons works out. S can have the ability to have an expanded octet, so it's totally fine. So how do you know which is the better of the two? Well, if you have more than one Lewis structure for the same thing and you're not 100% sure of how to decide which is the better of the two Lewis structures, there's something called formal charge that you can take a look at. Now, formal charge, what it does is it accounts for how the electrons are actually distributed in an atom. So when you draw your Lewis structure, we always talk about how the electrons don't care who they come to the party with. They just get distributed around to make the octet rule work. And that's true. But depending on how you draw your Lewis structure, sometimes that arrangement of electrons can either make more sense in how the physical properties of your elements are going to work or less sense. And so it can help us, like I said, in two ways. It can help us decide which of several Lewis dot structures is the one that makes the most sense for this real compound, or it can help us where we're going to see regions of electron charge, whether it's either positive because the electrons left or negative because there's extra electrons hanging out on that side, to see if that makes sense. That's going to play more of a role when we talk about molecular polarity coming on, but formal charge kind of takes care of both of those things. Formal charge is easy to calculate. What you have to do, and honestly, this is the hardest part, you have to be able to successfully count the number of valence electrons that your element brings to the party for the Lewis structure. And then what you do is you take a look at your final Lewis structure and you subtract all of the non-bonded electrons. That's those two dots that you see around your Lewis structure. You take away every dot, and then you take away the number of bonds. And I'll go through a couple of examples of this to make things clear. Things to keep in mind. Ideal structures for formal charge are going to have a minimal formal charge. So if at all possible, they're going to have a formal charge of 0 on everything. That's kind of the best case scenario. Negative formal charges should be sitting on elements that have higher electronegativity values, and positive formal charges should be able to sit on things that have less electronegativity. So things that don't want those electrons. If you remember, electronegativity is the willingness for an element to pull electrons towards itself in a bond. So we just want the electrons to be on things that want the electrons. Hopefully that makes sense. Okay, so here is our first example. I'm going to ask you to calculate the formal charge for all of the elements in carbon dioxide. So we are going to go through that, and I will work together with this example for you. So you just have to give me a minute here so I can get my doc cam up. So we've got CO2. Let me get my periodic table. And so the first thing that we need to do is we need to take a look at the Lewis structure. Now, sometimes you'll have to draw it. I gave you the Lewis structure for CO2. Okay, so I am going to take a look at how many different element kind of structures I have. And what I mean by that is if you look at the oxygens here, they're both connected in the same way. So we're an O double bonded to a carbon in both sides of this molecule. So I'm only going to do the formal charge calculation work for oxygen one time, and then carbon is its own thing. So what we're going to do, we'll start with oxygen because it's on the left-hand side here. Okay, oxygen has 8 electrons in it total, but if you remember valence electrons, it's 1, 2, 3, 4, 5, 6. So oxygen has 6 valence electrons. So to do a formal charge calculation, I'm going to do 6 to start off with because it has 6 valence electrons, okay? Then what I do is I subtract 1 number for every dot and 1 for every bond that's drawn in there. So if I look for my oxygen, I have 1, 2, 3, 4 dots and then 2 bonds. So I'm going to take away a total of 6 and I will end up with a formal charge of 0. So again, this 6 here comes from 4 electrons and then 2 bonds. Okay. This oxygen here has the same formal charge of 0 because it's identical to how the connections work on this oxygen. Okay. For carbon, we're going to do the same thing. So carbon here is going to have 4 valence electrons. And then if I look at how it's connected, I don't have any dots to subtract, but I do have 4 bonds. So I'm going to do -4, and that's going to give me a formal charge of 0 over here. Okay, so that's how you find the formal charge of something. Now, typically the formal charge is used to argue why one Lewis structure is better than another. So let's say you could draw carbon dioxide as, I mean, it would be, great, but you could draw it like this. Okay, so that is a potential way to draw that, but let's take a look at why that's not good. So now, do you see how we don't have 2 identical oxygens here? So I got to do the formal charge calculation. I start with 6 valence electrons that oxygen brings to the party, but in this situation, oops, I screwed up the Lewis structure on that. That's not great. Okay, there's only 2 dots there. Ignore my mess. Hold on. This is going to be confusing. Make those disappear. Like it never happened. Okay, so let's take a look at this oxygen here. It has 2 dots, so it's going to be -2, and then another 3 bonds, so -3 gives me a total of +1. So this oxygen has a formal charge of +1. Carbon starts off with 4 electrons, and I have 4 bonds, so I'm going to take away 4, and that's going to be 0 for the carbon. And then my formal charge for this oxygen is going to be 6 electrons that I start with, minus 1, 2, 3, 4, 5, 6 dots, and 1 bond gives me a -1. So this has a -1 for a formal charge. So what ends up happening is that the Lewis structure that we prefer is going to be one that has formal charges of 0 on all of its elements. If you can't get a formal charge of 0 in your Lewis structure, then you want the negatives to be on elements that have high electronegativity. So O is something that is okay with a high electronegativity or a negative charge. But in this case, the Lewis structure on the left here is better because it has formal charges of 0. Okay, hopefully that makes sense. All right, we are going to go to the next example. Okay, so I want you to try this one on your own before I go over it. So example number 2 says calculate the formal charge for all of the atoms in NO3. What element should have the extra negative charge on it? So what I want you to do is pause the video, take this Lewis structure, do the formal charge calculations for all of the atoms in there, and then we will see how things go. Okay? All right. Back to the doc cam. And now we have NO3. So we have a Lewis structure for NO3 with 1 double bond, and I don't remember if this is on the correct location, so just go with it. Okay, so the nitrate ion has a negative charge on it overall, but we want to calculate the formal charge for each of these in here. If you look, these O's are identical in how they are bonded, so we only have to do this calculation one time. We have to do it for the nitrogen and for this oxygen. So I'm going to do this oxygen first. Using my periodic table, oxygen brings 6 electrons to the party. I have 1, 2, 3, 4 electrons in there and 2 bonds, so that gives me a formal charge of 0. So this oxygen has a formal charge of 0. Okay. This oxygen and the other one also bring 6 electrons to the party, but if we take a look here, we have 6 dots around it, and then we have a bond, so our formal charge is going to be a -1, which means we have a -1 here, and we have a -1 for the formal charge here. Okay. The nitrogen, if we find nitrogen, brings 5 electrons to the table. I don't know why I put that down there. It's just 5. And then if we subtract the number of dots, there aren't any, but we do have 4 bonds, and so we have a formal charge of +1. Okay. Now, there are a lot of charges on here. You know, it's not the greatest, but it is what it is. What we have to do is see if the placement of the negative formal charges makes sense. So in this molecule, we see a +1 on the nitrogen and a -1 on the oxygen. If we compare these two here, the higher electronegativity element is going to be the oxygen, so it's okay because that oxygen has a -1 on it, and that's okay because it's the higher electronegativity. All right, we're going back to the presentation one more time, and I'm going to give you guys this one to try. I'll put it in a separate video. So I'm going back to that original question about H2SO4. What I want you to do is do the formal charge calculations for the atoms in each of these molecules. And then when you think you've got it figured out for which one is the better Lewis structure, come to the answer video and then we'll see if you got it correct. Okay. If you have any questions, make sure you hit me up in a Google Meet or in person, and we will see if we can get you a hand with things. All right. Good luck.